Alright, welcome back for more fun and games after Video Wednesday. That was fun. What are we doing today? First derivative test and Extrema. Alright, take a look at the following graph. Let's say I make up some wacky graph. Like that guy in the video, yeah. Where the heck are my lines? Okay, I don't like that one. I'll take this one. Yeah, it's the only one that has two arrows. Alright. So, let us say that I have a function that looks like this. Pretend that it actually is differentiable everywhere, okay? Yeah. It's supposed to be a smooth function, okay? Whoops. This pen sucks. So, there's your function, y equals f of x, whatever it is. Doesn't really matter what it is, exactly, I'm going to label it somewhere. Y equals f of x. There's your y-axis. There's the origin, there's your x-axis, okay? Alright, let me label this point A, and this point B, and this point C. Let's say, well, pretend there's a tangent line there, horizontal tangent line. And this point D. Okay, so there's my graph. What do you know about the derivative at A? The derivative of this function at A? Let's assume it's 0. Okay, it may not be a great drawing, but let's say there's horizontal tangent line there, right? So f prime at A is 0, f prime at B is 0, f prime at C, let's say it's 0, yeah, and at D it's 0, right? Okay, now realize that if this is a differentiable function, and automatically remember that differentiability implies continuity, it's continuous too, yes? There's nowhere else between A and B where the derivative is going to change sign. Here, what's the derivative? Any tangent line I draw here, what's the slope going to be, positive or negative? Positive. And the function is increasing, yes? Alright, so that's why we do a sign line test to figure out mins and maxes, first derivative test, because where the derivative is 0, between the zeros, it's got to be one sign, because it can't change sign unless it's another 0. So I know if it's increasing or decreasing, and I know if it's increasing or decreasing. Here it's definitely, without even graphing it, if I knew f prime, I would get f prime is what sign? Negative, right? So if I do a sign line test, and the derivative is 0 here, positive here, and negative there, you've got to get a max. If the derivative is negative 0, positive, you got to have a min. That's the first derivative test. Okay? So, what can I say? Well, I know that f prime of A is 0. And f is decreasing, f is decreasing for all x on the interval from negative infinity to what? Well, look at the graph again. F is decreasing for f, is decreasing for A, I'm saying it wrong. F is decreasing for x is what? Is it decreasing up to here, yes? So from negative infinity up to where? Up to A, that's all. Then it's increasing from A to B. That's what I'm just summarizing what we said. So since f prime of B is the next 0 for the derivative, f is increasing or decreasing from A to B. As it turns out, it's increasing. So for all x on the interval from A to B. Okay. And then from B to C, the function is decreasing, and from C to D, the function is increasing. From D to infinity, the function's decreasing. All right, so let's just summarize all that crazy stuff. F prime, if you're given f prime of C is 0, you know that f is decreasing for all x from B to C. Okay, from B to C, right? X goes from B to C, the function's decreasing. And f prime of D is 0, so f is increasing for all x from C to D. Right, from x goes from C to D, y is increasing, right? And then from then on, it's decreasing. That's just a description of this curve, since it's differentiable and continuous at all points. Didn't I give you an E? Oh, I'm sorry, I didn't give you that. All right, so whoops, go away. Thinking of something else. So it's decreasing from then on for all x from d to positive infinity. This is optional, but I always put a sign, or I tend to put a sign with infinity, even if it's not negative. I guess it's optional, but I just do it. Okay, so that hints at the first derivative test. Take a look at this graph. All right, let's get some axes. And let's say the curve looks like this. Let's see, what do we want? Okay, there's my curve. This is y, this is the origin, this is x, this is y equals f of x, a differentiable function everywhere, continuous everywhere, some polynomial probably. Okay? Now let's see. All right, now let me label this. A is this point. B is this point. C is this point. And D is this point. Okay? Oh, and I labeled this wrong. This is f prime. This is the derivative of the function. Okay? Before I had the function, now I have the derivative of the function. Let's say that's what it looks like. Okay? So this is the derivative. What do you know? Well, what is significant about this point? No, not here. That's the zero of the derivative, right? It could be maximum, I don't know yet, but I'm saying, isn't it a zero? Right. So it could represent a maximum for the function itself. I'll move this up a little bit. That's the question. If the function is differentiable and therefore continuous everywhere, okay, and the derivative is zero and changes sign, because the derivative doesn't have to change sign. I could have drawn it differently. I could have said it just bounces off the x-axis, say. It doesn't change sign. If it changes sign, now what's the derivative here? Remember, this is f prime, so f prime is positive and negative. Negative. And here? Positive. So it's changing from negative to positive. So I have a horizontal tangent line and a min. Yes? Then it's changing, here's a zero. It's changing from positive f prime to negative f prime. So here I have a horizontal tangent and a max. Here I have a min, here I have a max. Okay. All right, so let's summarize that. So what we're saying is that f prime is negative. F prime is negative when x is less than a, right? This part. And f prime is positive when x is greater than a. Well, I'm just saying near a. In a neighborhood about a. Forget about everybody else. Just near a. Okay? Then we're going to say that f of a is a relative min. Okay? Relative because it's only in this little neighborhood here. Okay? Until it changes sign again. So that's our conclusion. Now, how about at b? Well, f prime of x is greater than 0 when x is less than b, and f prime, sorry, it's greater than 0, right, this part, here. And f prime is negative here, so f prime of x is negative when x is greater than b. X is greater than b. So we're going to say that f of b is a what? Relative max. It may not be absolute unless you have endpoints to contend with. Remember the candidates theorem, we talked about that. Okay, so that's what we said. We'll have a relative min, a relative max, a relative min, and a relative max, right? Okay, so f prime, I'm just saying near b, okay? Near b, not near c, near b, this is true. Okay, so what I'm going to say about c? Well, f prime of x is less than 0 when x is less than c, and f prime of x is greater than 0 when x is greater than c. So it's decreasing, then it's increasing, and then there's a horizontal tangent when f prime is 0. So f of c is going to be a what? Relative min. And we can say the same thing at d. Positive, 0, negative, increasing, horizontal tangent, decreasing, it's got to be a max, right? So f prime is less than 0 when x is less than d. F prime is greater than 0 when, wait, I said it wrong. It's positive here, isn't it? Whoops, sorry. Greater than 0 and less than 0 when x is greater than d. So f of d is increasing, horizontal tangent, decreasing, max. And that's what the first derivative test says. All right. Now, do you know the second derivative test? All right. Let's take a look at the same graph, roughly. Yes, you think you do. Everybody says that the first time. Has nothing to do with concavity. Sorry. Has nothing to do with inflection. No. Oh, ye of little faith. Hang on. Okay. Let's say we have a similar graph of f prime. Say what? That would be incorrect. I've chosen my axis unwisely. Yeah, that was a Y. What the heck's going on there? Give me a pen. Okay. So it's similar to last time, right? So we have a 0 for f prime here. Now, first derivative. We have a 0 for f prime here. We have a 0 for f prime here. We have a 0 for f prime here. All right. Now, what's the derivative of the derivative? What's the second derivative look like? Well, when is the second derivative 0? I know when the first derivative is 0, here, here, and here. When's the second derivative 0? Right, at horizontal tangent lines of the first derivative, right? So from here to here, the second derivative is positive or negative? Positive. If I put a tangent line on the derivative function, I get positive slopes, right? That would be the second derivative, what that measures, this change of f prime, like an acceleration based on the velocity. All right. From this horizontal tangent to this horizontal tangent, the second derivative, or the slope of these tangent lines, are negative and positive and negative. Okay. Now look what happens. If, let's see, if f prime, wait, I'm saying this wrong. Okay. If f prime is 0, right? And f prime is negative, and then it's positive. What do you got? If f prime is negative, then 0, then positive, on a continuous function. Like here. No concavity. Right? I'm saying this. When you have a 0 in f prime, and f prime is negative, then it's positive, what do you have? A relative min on that curve. Right? Okay. The second derivative test says the same thing. When f prime is 0, but f double prime is positive. F prime is 0 here, right? F double prime is positive here, right? Now think concavity. If you're concave up at a horizontal tangent, the function must have a... No, the second derivative is not 0 here. The second derivative here is positive. The second derivative test says if the first derivative is 0, and at the same place the second derivative is positive, you have to have a relative min. Look at it. This is the function. The first derivative is 0, I have a horizontal tangent line. But the second derivative is positive, I'm concave up. It's got to be a min. First derivative is 0, I got a horizontal tangent line on the function, this is f. right? But the second derivative is giving me what concavity? Second derivative is negative. Concavity is concave down, yes? So if the second derivative is negative and the first derivative is 0, I got a max. If the second derivative is positive and the first derivative is 0, I got a min. If the first derivative is 0 and the second derivative is negative, I got a max. That's the second derivative test. It's another test for extrema, for mins and maxes. That's what it is. It's not really talking about inflection points, although you can get inflection points from the zeros of f double prime. That's something else. Whoops, too far. So let's summarize the second derivative test. It says, okay, we know that f prime at 0, f prime of a is 0. We know that f double prime at a is positive, slope of the tangent line here. So therefore, f of a has to be a relative min. So just looking at f prime, you can figure out f double prime, can't you? And knowing f prime and f double prime, you figure out mins and maxes. That's all you need. Okay, now f of b, f prime at b is 0, right? F double prime has a negative slope here, right? The tangent lines here are negative slopes. So, f of b is got to be a f prime is 0.
Okay.
Well, what do you think it was? No, this is 0. These are all zeros. 0, 0, 0. It's just a stupid pen. Okay. Yeah, f prime at b is 0, because this is f prime and that's a 0. F double prime at b is negative, because the slope of the tangent line here, the second derivative, the derivative of the derivative, is negative here. All right, so you have your concave down with a horizontal tangent, you've got a relative max. This is only true if the function is differentiable near b, continuous differentiable, all that fun stuff, and near a and so forth. All right, at c, what's our conclusion? Well, f prime at c is, f double prime at c is positive, so f of c must be positive concavity, concave up, horizontal tangent at the bottom. That's going to be a min. There you go. F prime at c is 0. F double prime at c is positive, greater than 0. Therefore, f of c is a relative min. So you use the first derivative test to find mins and maxes. You use the second derivative test to find mins and maxes. You need to know that. Some people don't realize that. I think the second derivative test has to do with inflection points. It doesn't. All right, and then we said that f prime at d is 0. F double prime at d is negative. So negative concavity, concave down, horizontal tangent, got to be a max. And it is. We're talking about this point right here. Okay? All right, we'll leave it at that. Goodbye. Nice to know you. Where are you?